Right now, at this very moment, as you sit there watching this video, you are spinning. You probably do not feel it. You probably think you are sitting perfectly still. But let me tell you something that will change the way you see yourself and your place in this universe forever. You are not still. You have never been still, not for a single second of your entire life. The chair you are sitting on, the floor beneath your feet, the building around you, the city you live in, the continent you call home, the entire planet Earth, all of it is spinning right now at roughly 1,670 kilometers per hour. That is faster than the speed of sound. You are on a giant spinning ball hurtling through space, and you do not even notice it. But here is where things start to get truly mind-bending. The Earth is not just spinning on its own axis, it is also orbiting the Sun at approximately 107,000 kilometers per hour. And the Sun itself is not standing still either. Our entire solar system is orbiting the center of the Milky Way galaxy at an astonishing 828,000 kilometers per hour. And the Milky Way, this enormous galaxy containing hundreds of billions of stars, is itself rotating. The whole thing, this vast cosmic pinwheel of stars and gas and dust, is spinning like a colossal carousel in the void of space. And even the Milky Way is not the end of the story. Our galaxy is part of a group of galaxies called the Local Group, and this group is moving through space as part of an even larger structure called the Laniakea supercluster. And these structures themselves show signs of rotation and organized motion. So let me ask you the question that should be keeping you up at night. Why? Why does everything rotate? Who told the Earth to spin? Who gave the Sun its orbit? Who set the galaxies turning? What force, what law, what cosmic principle decided that nothing in this universe would ever be allowed to stand still? This is not just a casual question. This is one of the deepest and most profound questions in all of physics. And in this video, we are going to answer it completely. We are going to go on a journey that starts at the very beginning of the universe itself, at the Big Bang. And we are going to trace the origin of rotation from that first moment all the way to the spinning of galaxies, the rotation of black holes, the bizarre quantum spin of subatomic particles, and everything in between. We are going to explore why planets spin, why some of them spin backward, why stars rotate, why they speed up when they die, why black holes are the ultimate spinners in the cosmos, and why even the fabric of spacetime itself gets dragged into rotation by massive spinning objects. We are going to dive into the mathematics, the physics, the astronomy, the quantum mechanics, and even the philosophy of rotation. And I promise you, by the end of this journey, you will never look at a spinning top, a turning wheel, or a starry night sky the same way again. But before we begin this deep journey, let me share with you some facts that will set the stage for just how extreme and universal rotation really is. There is a neutron star out there, a dead collapsed remnant of a massive star called PSR J1748-2446 AD. And this object is spinning at 716 rotations per second. Let that sink in. 716 times every single second. Its surface is moving at nearly a quarter of the speed of light. If you were standing on its equator, which of course you could not because you would be crushed by gravity billions of times stronger than Earth's, but if you could, you would be moving at roughly 70,000 kilometers per second. Now consider this. If the Earth suddenly stopped rotating, everything on the surface that was not bolted down to bedrock would be flung sideways at over 1,600 kilometers per hour. The atmosphere would continue moving even though the ground stopped, creating winds that would make any hurricane look like a gentle breeze. The oceans would slosh catastrophically, reshaping continents. The Earth's equatorial bulge would collapse, triggering earthquakes of unimaginable magnitude. And without rotation, our magnetic field would eventually die, leaving us exposed to the deadly radiation of the solar wind, which would slowly strip away our atmosphere, turning Earth into a dead world like Mars. Saturn spins so fast, completing a rotation in just 10.5 hours, despite being enormous, that it is visibly squashed. It is not a sphere. It is an oblate spheroid, wider at its equator than at its poles, because its own rotation is literally flinging its material outward. And at the quantum level, electrons possess something called spin, a property so fundamental and so strange that it does not correspond to actual physical spinning at all, and yet it behaves exactly like angular momentum in every experiment we can devise. An electron needs to rotate not 360 degrees, but 720 degrees, 2 full turns, to get back to its original state. There is nothing in our everyday experience that behaves like this. Nothing. And yet this property is so essential that without it, atoms could not form, chemistry would not exist, and you and I and everything we know would simply not be here. And here is perhaps the most astonishing fact of all. In the entire observable universe, across billions of light years of space, containing trillions of galaxies, each with hundreds of billions of stars, surrounded by planets and moons and asteroids and comets, down to the subatomic particles that make up every scrap of matter, there is not a single known object that has absolutely zero rotation. Not one. Everything spins. Everything rotates. Everything turns. Rotation is not an exception in the universe. It is the rule. It is the default state of existence. So if you are the kind of person who looks up at the stars and wonders why the universe is the way it is, if you are someone who finds beauty in understanding the deep mechanics of reality, then you are in exactly the right place. Hit that like button right now, because you are about to go on a journey that will fundamentally change how you understand the cosmos. Subscribe to this channel if you have not already, because we go this deep on every single topic. And leave a comment telling me, before you watch the rest of this video, what you think is the reason everything rotates. I want to hear your theories. I read every comment. Now let us begin at the very beginning. And when I say the very beginning, I mean the actual beginning. The origin of everything. To understand why everything in the universe rotates, we first need to understand what rotation actually is, because it is more subtle and more interesting than most people realize. When we say an object is rotating, we mean it is spinning around an axis. The Earth rotates around an axis that runs from the North Pole to the South Pole. A wheel rotates around its axle. A figure skater rotates around a vertical axis through their body. This is rotation, spinning around an internal axis. But rotation is different from revolution. Revolution is when an object moves in an orbit around something else. The Earth revolves around the Sun. The Moon revolves around the Earth. These are different motions, and it is important to keep them straight, because both are happening simultaneously, and both have the same deep origin, but they are governed by slightly different aspects of the same physics. Now here is the key concept that underlies all of rotation, and I mean all of it, from the spin of galaxies down to the spin of electrons. It is called angular momentum. Angular momentum is to rotation what regular momentum is to straight line motion. When a car is moving in a straight line, it has linear momentum. The heavier the car and the faster it moves, the more momentum it has. Angular momentum is the rotational equivalent. The more massive an object, the wider it is, and the faster it spins, the more angular momentum it has. The exact formula involves the moment of inertia, which describes how an object's mass is distributed relative to its axis of rotation, multiplied by the angular velocity, which is how fast it is spinning. But the formula is not the most important thing here. The most important thing is what angular momentum does, or rather what it does not do. It does not change. Not unless something external forces it to change. This is the law of conservation of angular momentum, and it is one of the most ironclad, unbreakable laws in all of physics. It says that in a closed system, where no external torques are acting, the total angular momentum remains constant. It cannot increase. It cannot decrease. It is conserved. This is not a suggestion. This is not an approximation. This is an absolute law of nature. and it has never been violated in any experiment ever conducted in the history of science. Let me give you the most famous everyday example. Imagine a figure skater spinning on ice. She starts with her arms stretched out wide, spinning slowly. Then she pulls her arms in close to her body. What happens? She spins faster. Much faster. Her angular momentum has not changed because no external torque was applied, but her moment of inertia decreased because her mass is now closer to her axis of rotation. So to keep angular momentum constant, her angular velocity had to increase. She spins faster. This is not a trick. This is not an illusion. This is conservation of angular momentum in action, and it is the exact same principle that governs why neutron stars spin hundreds of times per second, and why collapsing gas clouds become spinning solar systems. The skater and the neutron star are obeying the same law. Now there is another concept we need, and that is torque. If force is what causes linear acceleration, torque is what causes rotational acceleration. Torque is a twisting force. When you turn a wrench, you apply torque. When you open a door by pushing on the handle farthest from the hinge, you are applying torque. Torque can start rotation, stop rotation, speed it up, slow it down, or change its direction. But here is the critical point. In the vast emptiness of space, there is very little to apply torque to anything. There is no friction. There is no air resistance. There is nothing to grab onto. So once something in space starts rotating, it tends to keep rotating essentially forever. The only things that can apply torque to objects in space are gravitational interactions with other objects, magnetic fields, and radiation pressure, and these forces, while real, are often extremely weak compared to the angular momentum they would need to overcome. This is why rotation is so persistent, so enduring, so everywhere. Once it starts, the universe has almost no way to stop it. There is one more point about rotation that is deeply important and somewhat surprising. In a three-dimensional universe like ours, rotation is essentially inevitable for any object that forms through the gravitational collapse of a cloud of material. Think about it this way. For a cloud of gas and dust to collapse under gravity and form a star or a planet with absolutely zero rotation, every single particle in that cloud would need to be falling directly toward the center, perfectly radially inward, no sideways motion at all. The probability of this happening is essentially zero. In fact, it is mathematically zero. Any tiny random motion, any slight asymmetry, any gentle nudge from a passing gravitational wave or a nearby star, or even quantum fluctuations, will give the collapsing material a net sideways motion. And that sideways motion, when you add it all up over trillions of particles falling inward, becomes rotation. It becomes angular momentum. And once it exists, conservation of angular momentum ensures it will persist and even intensify as the collapse continues. So rotation is not something special that needs to be explained by some exotic mechanism. It is the natural, inevitable, unavoidable consequence of gravity acting on anything that is not perfectly symmetric. And nothing in nature is perfectly symmetric. Now let us go back to the very beginning of everything. 13.8 billion years ago, the universe as we know it came into existence in an event we call the Big Bang. Now I want to be very careful here because the Big Bang is one of the most misunderstood concepts in all of science. Most people picture the Big Bang as a giant explosion, like a bomb going off in empty space, with matter and energy flying outward in all directions. But that is not what happened. There was no empty space for the explosion to happen in. There was no outside for things to fly into. The Big Bang was not an explosion of matter into space. It was an expansion of space itself. All of space, all of time, all of matter, all of energy, everything that exists was compressed into an unimaginably hot, unimaginably dense state. A singularity. A point of infinite density and infinite temperature where the laws of physics as we know them break down completely. And then, for reasons we still do not fully understand, This singularity began to expand. Space itself began to stretch, carrying matter and energy with it. And it has been expanding ever since. In the first fraction of a second, things happen so fast and at such extreme conditions that our understanding becomes hazy. In the first 10 to the minus 43 seconds, the Planck epoch, all four fundamental forces were unified and quantum gravity effects dominated. We do not have a theory of quantum gravity yet, so we cannot say with certainty what happened during this time. Then, as the universe cooled slightly, the forces began to separate. Gravity split off first, then the strong nuclear force. And during this separation, something extraordinary happened. The universe underwent a period of inflation, an exponential expansion so rapid that the observable universe went from smaller than a proton to larger than a grapefruit in a tiny fraction of a second. This inflation is crucial to our story because it took tiny quantum fluctuations at the subatomic scale, and stretched them to cosmic scales. These quantum fluctuations became the seeds of all structure in the universe. They became the slight density variations that would eventually grow into galaxies, galaxy clusters, and the entire cosmic web of large-scale structure. And, most importantly for our story, they became the seeds of angular momentum. The seeds of rotation. Now here is the question that goes to the heart of everything. Did the Big Bang itself rotate? This is not a silly question. In 1949, the legendary mathematician and logician Kurt Gödel, who was a close friend of Albert Einstein at the Institute for Advanced Study in Princeton, found an exact solution to Einstein's field equations of general relativity that described a rotating universe. In Gödel's solution, the entire universe rotates as a whole. Every point in space is rotating relative to distant matter, and this solution had an extraordinary and disturbing consequence. In a rotating universe, there exist paths through spacetime called closed time-like curves, paths that loop back on themselves in time. In plain language, Gödel's rotating universe allows time travel. You could, in principle, travel along one of these paths and arrive back at your own past. Einstein was reportedly deeply troubled by this discovery. His own theory of general relativity, his masterpiece, the crowning achievement of his scientific life, allowed for the possibility of time travel if the universe rotated. Gödel reportedly presented this result to Einstein as a birthday gift. Some gift. Now, does our actual universe rotate? Current observations suggest that if it does, the rotation is incredibly small. Scientists have searched the cosmic microwave background radiation, the afterglow of the Big Bang, for signs of universal rotation. If the universe were rotating, it would produce a specific pattern in the CMB, a particular kind of asymmetry that we could detect. So far, the CMB appears to be remarkably isotropic, meaning it looks essentially the same in every direction. This puts a very tight limit on any possible universal rotation. If the universe is rotating, it is doing so at less than about 10 to the minus 9 radians per year, which is extraordinarily slow. But extraordinarily slow is not the same as zero, and this question remains open. There is also a tantalizing and controversial observation. In 2011, physicist Michael Longo at the University of Michigan analyzed over 170,000 spiral galaxies and found a slight excess of galaxies that appeared to spin in one direction compared to the other. If the universe had no preferred rotational direction, you would expect exactly half the galaxies to spin clockwise and half to spin counterclockwise. But Longo found a small but statistically significant preference for one direction over the other. If this result holds up, it could be a hint that the universe has a net angular momentum, a preferred rotational direction. Subsequent studies have both supported and contradicted this finding, and the question remains one of the most intriguing open problems in cosmology. But here is the thing. Whether or not the universe as a whole rotates, the origin of rotation within the universe is well understood, and it comes down to something beautifully simple. Imperfection. The universe was never perfectly uniform. From the very first instant, quantum fluctuations ensured that the distribution of matter and energy was slightly uneven. Some regions were a tiny bit denser than others, some regions were a tiny bit less dense. And when gravity began to pull matter together, these density differences meant that the collapsing material was never falling inward in a perfectly symmetric way. There was always a slight asymmetry, a slight imbalance, a slight sideways component to the motion of the infalling material. And this sideways component, when summed up over an entire collapsing cloud of matter, produced a net angular momentum. A net rotation. This is the tidal torque theory, and it is the leading explanation for how the first large-scale structures in the universe acquired their rotation. As protogalactic clouds began to collapse under gravity in the early universe, they were not isolated. They were surrounded by other collapsing clouds, each with its own gravitational pull. These neighbouring structures exerted tidal forces on each other, forces that were not uniform, forces that pulled harder on one side of a cloud than the other. These tidal forces created torques, twisting forces that gave the collapsing clouds their initial angular momentum. Think of it like this. Imagine you are in a swimming pool, and two people on either side of you start creating currents by moving their arms. The currents from one side push you in one direction, and the currents from the other side push you in a slightly different direction. The net effect is that you start to spin. Not because anyone intended to make you spin, but because the forces acting on you were not perfectly balanced. This is essentially what happened in the early universe, but with gravitational forces instead of water currents, and with enormous clouds of gas instead of a person in a pool. The beauty of this explanation is that rotation is not something that needs to be specially created or injected into the universe by some external mechanism. It arises naturally, inevitably, and spontaneously from the simple fact that the universe is not perfectly uniform. And thanks to conservation of angular momentum, once this rotation is created, it persists forever unless something actively works to eliminate it. And in the vast emptiness of space, there is very little that can do that. So now we have the origin. We know where the first rotation came from. It came from the gravitational collapse of slightly non-uniform matter in the early universe, given its initial angular momentum by tidal torques from neighbouring structures and by the primordial quantum fluctuations that seeded all cosmic structure. Now let us follow this rotation forward in time and see how it manifested at every scale of the cosmos, starting with the objects most familiar to us, the planets. 4.5 billion years ago, in a relatively quiet region of the Milky Way galaxy, there existed an enormous cloud of gas and dust called a molecular cloud. This cloud was mostly hydrogen and helium, with small amounts of heavier elements that had been forged in the nuclear furnaces of previous generations of stars and scattered into space by their explosive deaths. This cloud was vast, spanning many light years across, and it was cold, just a few tens of degrees above absolute zero, and for a long time it just sat there, held up against its own gravity by internal gas pressure and turbulence. But then something disturbed it. Perhaps a shockwave from a nearby supernova explosion rippled through the cloud, compressing some regions just enough to tip them over the edge. Perhaps a passing star's gravity nudged a portion of the cloud to slightly higher density. Whatever the trigger, a region of the cloud began to collapse under its own gravity. As it collapsed, it drew in more and more material, growing denser and denser at the center. And because this cloud, like everything in the universe, was not perfectly still, because it had some tiny amount of random internal motion, it had a small but non-zero angular momentum. As the cloud contracted, conservation of angular momentum kicked in. Just like the figure skater pulling in her arms, the shrinking cloud spun faster and faster. The slight, almost imperceptible rotation of the original vast cloud was amplified enormously as the material compressed down to a much smaller size. And something else happened that is absolutely crucial to the story. The collapsing cloud flattened into a disk. This might seem puzzling at first. Why would a roughly spherical cloud of gas turn into a flat disk? The answer is elegant. Consider all the particles in the collapsing cloud. They are all falling inward, but they also have random velocities in all directions. Particles moving up and down, perpendicular to the plane of rotation, collide with particles moving in other directions. These collisions cancel out the vertical motions through energy dissipation. But the motion in the plane of rotation, the rotational motion, cannot be cancelled out, because that would violate conservation of angular momentum. So the vertical motions get dissipated by collisions, but the rotational motions are preserved. The result is that the cloud naturally settles into a thin, flat, rotating disk. This is the protoplanetary disk, and it is the nursery where planets are born. And this, by the way, is why the solar system is flat. It is why all the planets orbit the Sun in roughly the same plane. They are all children of that original rotating disk. Within this swirling disk, the process of planet formation began. Tiny grains of dust collided and stuck together through electrostatic forces. These small clumps grew into larger clumps. The larger clumps grew into boulders. The boulders grew into planetesimals, objects a few kilometers across. And the planetesimals collided and merged to form protoplanets. Each of these collisions added angular momentum to the growing body. Some collisions would spin it up in one direction, others in the opposite direction. But because most of the material in the disk was orbiting in the same direction as the original cloud's rotation, most collisions tended to add angular momentum in the same direction. The net result was that the planets ended up spinning in the same direction that they orbit the Sun. This is called prograde rotation, and it is the case for most of the planets in our solar system. Think of the formation of a planet as a cosmic roulette wheel. Every collision with a planetesimal or a chunk of debris is like a ball hitting the wheel. Some hits spin it one way, some spin it the other way. But because the roulette wheel is sitting on a table that is already tilted in one direction, most of the hits come from one side, so the net spin ends up in that preferred direction. That is why Jupiter, Saturn, Mars and Earth all spin counterclockwise when viewed from above their north poles, the same direction they orbit the Sun. The tilt of the table, so to speak, was the original rotation of the solar nebula. But not every planet got the memo, and this is where the story gets really interesting. Venus, our closest planetary neighbour, the planet most similar to Earth in size and composition, rotates backward. It spins clockwise when viewed from above its north pole, the opposite direction from nearly every other planet in the solar system. And not only does it rotate backward, it rotates incredibly slowly. A single day on Venus takes 243 Earth days. Its year, the time it takes to orbit the Sun, is only 225 Earth days. Venus's day is longer than its year. This is deeply bizarre, and explaining it has been one of the enduring challenges of planetary science. There are several theories. The most dramatic one is that early in Venus's history, when the planets were still forming and the inner solar system was a chaotic shooting gallery of collisions, Venus was struck by a massive impactor, something perhaps as large as Mars. This impact was so energetic that it reversed Venus's rotation entirely, knocking it from prograde to retrograde spin. This is not as far-fetched as it might sound. We know that giant impacts were common in the early solar system. The Moon itself is thought to have formed from the debris of such a collision between the early Earth and a Mars-sized body called Theia. A similar collision could have flipped Venus. But there is another theory that is perhaps even more fascinating. It is possible that Venus's thick, dense atmosphere, which is about 90 times denser than Earth's, played a role. The Sun's gravitational tidal forces acting on Venus's dense atmosphere could have created thermal tides, atmospheric tides driven by solar heating, that gradually slowed Venus's rotation, brought it to a stop, and then pushed it into slow retrograde rotation. In this scenario, Venus was not knocked backward by a single catastrophic event, but was slowly, gently, relentlessly dragged into backward rotation by the patient, persistent tug of the Sun on its atmosphere over hundreds of millions of years. Recent computer simulations suggest this atmospheric tidal mechanism is actually quite effective, and many planetary scientists now lean toward this explanation, though the question is far from settled. And then there is Uranus, which presents an even stranger case. Uranus does not spin backward or forward, it spins sideways. Its axial tilt is 98 degrees, meaning its rotation axis is nearly in the plane of its orbit. It is essentially rolling around the Sun on its side. During its 84-year orbit, each pole alternately points almost directly at the Sun, meaning each hemisphere gets roughly 42 years of continuous sunlight followed by 42 years of darkness. This is extraordinary, and it demands an explanation. The leading theory is that early in the solar system's history, Uranus was struck by one or more large protoplanets that knocked it onto its side. Simulations show that a single impact from an Earth-sized body could have done the job. But there are problems with this simple picture. A single giant impact should have also affected Uranus's moon system, tilting their orbits in predictable ways. But the moons of Uranus orbit neatly in the plane of Uranus's tilted equator, as if they formed after the tilt event. This has led some researchers to propose that the moons formed from a debris disk created by the impact, similar to how our moon formed. Others suggest that a series of smaller impacts, rather than one big one, gradually tilted Uranus over. And still others have proposed that a large ancient moon, long since lost, could have gravitationally interacted with Uranus to cause the tilt. This remains an active area of research, and new computer simulations continue to refine our understanding. Now let us talk about our own planet's rotation, because Earth's spin has a remarkable story of its own. When the Earth first formed, about 4.5 billion years ago, it was spinning much faster than it is today. The best estimates suggest that a day on the early Earth was only about 6 to 8 hours long. Imagine that. Sunrise to sunset in about 3 hours. The sky would have wheeled overhead at a dizzying pace. The reason Earth spun so fast initially is the same reason everything spins fast when it is freshly formed. Conservation of angular momentum from the accretion process. But then, something dramatic happened. About 50 to 100 million years after Earth formed, a body roughly the size of Mars, which we call Theia, slammed into the young Earth in a cataclysmic collision. This impact was so violent that it partially melted both bodies, ejecting a vast amount of debris into orbit around Earth. This debris eventually coalesced to form the Moon. The impact itself significantly affected Earth's rotation, though the exact details depend on the angle and velocity of the impact, which are still debated. Some models suggest Theia actually sped up Earth's rotation, others suggest it slowed it down, and the net effect depends on assumptions about the impact geometry. But regardless of the immediate effect, the formation of the Moon set in motion a process that has been slowing Earth's rotation ever since. That process is tidal friction. Here is how it works. The Moon's gravity pulls on the Earth, creating tidal bulges in the oceans. The water on the side of Earth closest to the Moon is pulled toward the Moon, creating a high tide. The water on the opposite side of Earth is also pulled into a bulge, because the solid Earth beneath it is being pulled more strongly toward the Moon than the water on the far side. These tidal bulges are not perfectly aligned with the Earth-Moon line, because Earth is rotating. The rotation carries the bulges slightly ahead of the Moon in its orbit, because Earth rotates faster than the Moon orbits. Now these displaced tidal bulges have their own gravitational pull, and they pull the Moon slightly forward in its orbit, giving it energy and pushing it to a higher orbit. This is why the Moon is slowly moving away from Earth, at about 3.8 centimeters per year. But there is a cost. The energy given to the Moon has to come from somewhere, and it comes from Earth's rotational energy. The same tidal interaction that pushes the Moon away also applies a braking torque on Earth's rotation, slowing it down. This is happening right now. Earth's rotation is slowing by about 2.3 milliseconds per century. That sounds tiny, and it is, but over geological time, it adds up enormously. 600 million years ago, during the Cambrian period when complex life first appeared, a day was only about 21 hours long. There were over 400 days in a year. We know this from the growth rings of ancient coral fossils, which record daily and seasonal growth patterns, allowing us to count the number of days in a year. Going further back, when the moon first formed, it was much closer to Earth and the tidal forces were much stronger. So Earth's rotation was slowing much faster than it is today, and this process will continue into the far future. Eventually, in tens of billions of years, Earth's rotation will slow to the point where a day is as long as a month, the same time it takes the moon to orbit Earth. At that point, the same face of Earth will always point toward the moon, and the same face of the moon will always point toward Earth. This is called mutual tidal locking, and it has already happened with the moon. The moon is already tidally locked to Earth, which is why we always see the same face of the moon. It is not that the moon does not rotate, it does rotate. But it rotates at exactly the same rate as it orbits, so the same face always points toward us. This is not a coincidence. It is the inevitable result of tidal friction operating over hundreds of millions of years. Tidal locking is extremely common in the universe. Most of the large moons of the solar system are tidally locked to their parent planets, and in the Pluto-Charon system, both bodies are tidally locked to each other, always showing the same face to their partner. Pluto and Charon are caught in an eternal gravitational gaze, forever facing each other as they waltz around their common center of mass. This has profound implications for the search for habitable exoplanets, because many rocky planets orbiting red dwarf stars, which are the most common type of star in the galaxy, are expected to be tidally locked. One side always faces the star, baking in perpetual daylight. The other side faces away, locked in eternal darkness and extreme cold. The habitability of such worlds depends critically on whether their atmospheres can redistribute heat from the day side to the night side, a question that atmospheric scientists and climate modelers are actively investigating. Now let us consider the gas giants, because their rotation tells us something important about how size and composition affect spin. Jupiter, the largest planet in our solar system, has the shortest day. Despite being more than 300 times the mass of Earth and having a diameter more than 11 times greater, Jupiter completes a full rotation in just 9 hours and 56 minutes. Saturn is similar, with a day of about 10 hours and 42 minutes. These are stunningly fast rotation rates for such enormous objects. Compare that to Earth's 24 hours or Venus's 243 days. Why do the gas giants spin so fast? Several factors contribute. First, they are massive and formed from a much larger volume of the original nebula. More material means more angular momentum captured during accretion. Second, and perhaps more importantly, gas giants have no solid surface to create friction. The interior of Jupiter is a swirling fluid of hydrogen and helium, transitioning from gas to liquid to exotic metallic hydrogen under tremendous pressure. Without a solid surface, there is very little internal friction to dissipate rotational energy. Rocky planets like Earth lose rotational energy through tidal friction between their solid crusts and their liquid interiors, and through ocean tides. Gas giants have no such mechanism, at least not to the same degree. Third, gas giants likely experienced significant gravitational contraction after their initial formation, pulling in their extensive gas envelopes over millions of years. This contraction, just like the figure skater pulling in her arms, would have increased their rotation rate. Jupiter also displays a remarkable phenomenon called differential rotation. Its equatorial regions rotate faster than its polar regions. The equator completes a rotation in about 9 hours and 50 minutes, while the poles take about 9 hours and 55 minutes. This is possible because Jupiter is fluid, not solid. Different latitudes can rotate at different speeds. The Sun does the same thing, and so do the other gas giants. This differential rotation drives complex weather patterns and is responsible for Jupiter's famous bands of clouds and its great red spot, a storm that has been raging for hundreds of years, itself a magnificent example of rotation within rotation. Now let us leave the planets behind and venture into the realm of stars, because the rotation of stars reveals some of the most beautiful physics in the cosmos. Stars form from the same process that forms planets, just on a larger scale. A region of a molecular cloud becomes gravitationally unstable and begins to collapse. The collapsing cloud has some angular momentum, so it spins faster as it contracts. The central region becomes a protostar, while the surrounding material forms a disk from which planets may eventually form. Young stars, in the T Tauri phase of their lives, rotate quite rapidly, typically completing a rotation in a few days. This makes sense because they have recently formed from collapsing clouds and have concentrated their angular momentum into a relatively small volume. Our Sun, however, rotates much more slowly, taking about 25 days to complete a rotation at its equator and about 35 days at its poles. Why is the Sun so much slower than a young star? The answer involves one of the most elegant mechanisms in astrophysics, a process called magnetic braking. Stars like the Sun have magnetic fields, and they also have stellar winds, streams of charged particles flowing outward from the star into space. The star's magnetic field extends out into the stellar wind, and because the charged particles of the wind are forced to follow magnetic field lines, the magnetic field acts like a lever arm connecting the star to its wind. As the stellar wind flows outward, it carries angular momentum away from the star, gradually slowing its rotation. This is like spinning in a swivel chair while holding a long pole. If someone grabs the end of the pole, you slow down because angular momentum is being transferred from you to them through the pole. The magnetic field is the pole, and the stellar wind is the person grabbing it. This process, magnetic braking, operates throughout a star's main sequence lifetime, the long phase during which it burns hydrogen in its core. Over billions of years, it gradually spins the star down from the rapid rotation of its youth to the sedate rotation of its old age. The Sun has been undergoing magnetic braking for 4.6 billion years, which is why it now rotates relatively slowly. This relationship between age and rotation is so reliable that astronomers have developed a technique called gyrochronology, which allows them to estimate a star's age simply by measuring how fast it spins. A rapidly rotating Sun-like star is young. A slowly rotating Sun-like star is old. Spin becomes a cosmic clock. But here is something that puzzled astronomers for decades, something called the angular momentum problem of star formation. When you calculate the angular momentum of a typical molecular cloud core, the region that will collapse to form a star, and then compare it to the angular momentum of the resulting star, there is a huge discrepancy. The cloud core has far more angular momentum than the star. Where did all that angular momentum go? The answer is beautiful. The angular momentum did not disappear. It was transferred, redistributed, shared with other components of the system. Some angular momentum was carried away by bipolar jets, powerful streams of material that shoot out from the poles of the forming star at hundreds of kilometers per second. These jets are ubiquitous in star-forming regions and are directly observed. Some angular momentum was transferred to the protoplanetary disk surrounding the young star. And some angular momentum was stored in the orbital motions of any planets or companions that formed from the disk. In other words, the reason solar systems exist, the reason planets orbit stars, is in large part because the star needed somewhere to dump its excess angular momentum. Planets are, in a very real sense, angular momentum dumps. The solar system exists because the Sun could not keep all the angular momentum from the cloud that formed it. It had to share, and that sharing created the orbiting worlds we call home. More than half of all stars in the galaxy exist not as single stars like our Sun, but as binary or multiple star systems, two or more stars orbiting each other. Binary star systems store enormous amounts of angular momentum in their mutual orbits. The orbital angular momentum of a binary star system is often much greater than the spin angular momentum of either star individually. Binary formation is another way the universe deals with the excess angular momentum problem. When a cloud core has too much angular momentum to form a single star, it fragments into two or more pieces, each of which becomes a star, and the excess angular momentum is stored in their orbital motion around each other. Among the most extreme stellar rotators are the B stars, massive hot stars that spin so incredibly fast that they are on the verge of flying apart. The E and B stands for emission, because these stars emit light from disks of material that they fling off their equators. They are rotating at a significant fraction of their breakup velocity, the speed at which centrifugal force at the equator equals the gravitational force holding the star together. One of the fastest known spinning stars is Vefts 102, located in the Large Magellanic Cloud, which rotates at about 600 kilometers per second at its equator. For comparison, our Sun's equatorial rotation speed is only about 2 kilometers per second. Vefts 102 is spinning 300 times faster than the Sun. At this speed, the star is oblate, stretched into a pumpkin shape, with its equator significantly wider than its poles. If it was spinning just a bit faster, it would tear itself apart. These extreme rotators are thought to have been spun up by mass transfer from a binary companion or by a merger with another star. Now comes one of the most dramatic and awe-inspiring chapters in the story of cosmic rotation. What happens when a star dies? For most of their lives, stars are in a state of balance. The inward pull of gravity trying to compress the star is exactly balanced by the outward push of energy generated by nuclear fusion in the core. But fusion fuel is finite. Eventually, the core runs out of hydrogen, and for massive stars, it runs through heavier and heavier elements until it reaches iron. Iron is the end of the line for nuclear fusion, because fusing iron requires energy rather than releasing it. At that point, the core has no more energy source to support itself against gravity. And in a catastrophic instant, the core collapses. For a star between about 8 and 25 solar masses, the core collapse does not stop until the matter is compressed to nuclear density. Protons and electrons are squeezed together to form neutrons. The entire core, originally the size of Earth, is compressed down to a ball about 20 kilometers in diameter. This is a neutron star, one of the most extreme objects in the known universe. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is about 200 billion times stronger than Earth's. And here is where angular momentum conservation produces one of the most spectacular results in all of astrophysics. Remember our figure skater pulling in her arms? Now imagine that, but instead of a human pulling in their arms, you have a stellar core the size of Earth compressing down to a ball the size of a city. The factor of compression is enormous, roughly 100,000 to 1 in radius. Angular momentum is conserved, so the moment of inertia decreases by a factor of roughly 10 billion, and the rotation rate increases by the same factor. If the original stellar core was rotating once per day, which is typical, the resulting neutron star will be rotating roughly 10 times per second. Some are even faster, depending on the core's initial spin. This is why newborn neutron stars are such rapid spinners. They are not being driven by any engine. They are simply the compressed remnants of much larger rotating objects, spinning fast because angular momentum demanded it. Pulsars are neutron stars that we can see because their magnetic fields channel radiation into beams that emanate from their magnetic poles. As the neutron star rotates, these beams sweep around like the beams of a lighthouse. If one of these beams happens to sweep across Earth, we detect a regular pulse of radio waves, 1 pulse per rotation. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University, working with her advisor Anthony Hewish. When she first detected the regular pulses, they were so precise and so unnatural seeming that the team briefly considered the possibility that they were signals from an extraterrestrial civilization. They jokingly named the first pulsar LGM-1 for Little Green Men. Of course, it turned out to be a rapidly rotating neutron star, but the discovery was no less extraordinary for being natural rather than artificial. Pulsars are among the most precise clocks in the universe, rivaling the best atomic clocks in their regularity. Hewish received the Nobel Prize in Physics in 1974 for this discovery, though controversially, Bell Burnell was not included, a decision that remains one of the most debated in the history of the Nobel Prize. But the story of neutron star rotation does not end with their birth. Some pulsars have been spun up to even more extreme rotation rates through a process called recycling. Here is how it works. If a neutron star exists in a binary system with a companion star, and the companion star evolves and expands, material from the companion can flow onto the neutron star. This material does not fall straight down. Because the binary system is orbiting, the infalling material has angular momentum and it spirals inward, forming an accretion disk around the neutron star. As this material eventually lands on the neutron star's surface, it transfers its angular momentum to the neutron star, gradually spinning it up. Over millions of years, this accretion process can spin the neutron star up to astonishing speeds, creating what we call millisecond pulsars. The fastest known pulsar is PISA J1748-24468, located in a globular cluster called Terzan 5. This tiny remnant of a dead star, barely 20 kilometers across, rotates 716 times every single second. Its equatorial surface is moving at about 24% of the speed of light, roughly 70,000 kilometers per second. The centrifugal forces at its surface are mind-boggling. If you could somehow stand on the equator of this neutron star, which you obviously could not, because you would be instantly crushed into a thin film of subatomic particles by the intense gravity. But if you could, you would be flung outward at roughly 1/4 the speed of light. The only thing keeping the neutron star from flying apart is the incredible strength of the nuclear forces binding its neutrons together. If it were spinning just a bit faster, even these forces could not hold it together, and it would disintegrate. There is a theoretical maximum rotation rate for neutron stars called the mass shedding limit, or Kepler frequency. At this rate, the centrifugal force at the equator exceeds gravity and material begins to fly off the surface. For a typical neutron star, this limit is somewhere around 1,000 to 2,000 rotations per second, depending on the exact equation of state of nuclear matter at extreme densities, which is still uncertain. The fact that we observe pulsars spinning at 716 times per second, but not at say 2,000 times per second, provides constraints on the properties of ultra-dense matter, which is information we cannot obtain any other way. Pulsars are natural laboratories for extreme physics, and their rotation is the key to unlocking their secrets. Among the most extraordinary neutron stars are magnetars, neutron stars with the most powerful magnetic fields in the known universe. A typical magnetar has a magnetic field of about 10 to the 15th Gauss, which is about a quadrillion times stronger than Earth's magnetic field and roughly 1,000 times stronger than a typical neutron star's already intense field. To put this in perspective, if a magnetar were located at the distance of the Moon, its magnetic field would erase every credit card on Earth. These phenomenal magnetic fields are generated by a dynamo mechanism powered by the neutron star's rotation. When a neutron star is born spinning very rapidly, the combination of rapid rotation and the highly conducting neutron fluid in its interior can amplify magnetic fields to extraordinary strengths, much like a dynamo generates electricity, but on an incomprehensibly more powerful scale. The rapid rotation is essential. Without it, the dynamo mechanism could not operate, and magnetar strength fields could not be generated. Once again, rotation is the key. Magnetars produce some of the most energetic events in the universe. Their intense magnetic fields stress the rigid crust of the neutron star, and periodically the crust cracks in events called starquakes, releasing enormous bursts of energy. On December 27, 2004, a magnetar called SER 1806-20, located about 50,000 light-years from Earth, produced a giant flare that was the brightest event from outside our solar system ever recorded. In just 0.2 of a second, it released as much energy as the Sun produces in 250,000 years. The flash was so bright that it disturbed Earth's ionosphere, despite coming from the other side of the galaxy. If this magnetar had been within about 10 light-years of Earth, it would have been an extinction-level event, stripping away our ozone layer and bathing the surface in lethal radiation. When massive stars die in supernova explosions, the explosions are often not perfectly symmetric. One side might blow out slightly more forcefully than the other. This asymmetry gives the resulting neutron star a kick, a velocity boost that sends it hurtling through space. Some neutron stars have been observed moving at speeds of over 1,000 kilometers per second relative to their surroundings. And the asymmetric explosion can also impart or modify the neutron star's spin. So we have these objects, incredibly dense, incredibly magnetic, spinning hundreds of times per second, and hurtling through the galaxy at incredible speeds. They are among the most extreme objects nature has ever produced, and every aspect of their extremity, their density, their magnetic fields, their speed, is connected in one way or another to rotation. But neutron stars, as extreme as they are not the ultimate spinners. That title belongs to black holes. When the most massive stars die, or when matter accumulates beyond a certain threshold, even the nuclear forces binding neutrons together cannot resist the pull of gravity. Everything collapses past the point of no return, and a black hole is formed. A black hole is an object so dense that nothing, not even light, can escape its gravitational grip once it crosses the event horizon, the boundary of no return. Now here is a fact that is absolutely central to our story. Every black hole in the universe spins. And we know this not as a theoretical speculation, but as an observational fact. We have measured the spins of numerous black holes using X-ray observations of their accretion disks, and, more recently, using gravitational wave signals from merging black holes. And not a single one has been found to have zero spin. This makes perfect sense when you think about it. Black holes form from the collapse of rotating objects, whether they are massive stellar cores or accumulations of matter spiraling inward. Conservation of angular momentum guarantees that the resulting black hole will rotate. And given the extreme compression involved, the rotation will be extreme. The physics of rotating black holes is described by the Kerr metric, a solution to Einstein's field equations discovered by New Zealand mathematician Roy Kerr in 1963. Kerr's solution is considered one of the most important exact solutions in general relativity, and its discovery was a landmark moment in theoretical physics. A non-rotating black hole, described by the Schwarzschild metric, is relatively simple. It has an event horizon, a singularity at the center, and nothing else. But a rotating black hole, a Kerr black hole, is far more complex and far more interesting. A Kerr black hole has a spin parameter, usually denoted by the letter A. That ranges from 0 for no rotation to 1 for the maximum possible rotation. At A equals 1, the event horizon itself is effectively rotating at the speed of light. Real astrophysical black holes have been measured with spin parameters frighteningly close to this maximum. The black hole in the system GIARS 1915 plus 105 has a measured spin parameter of about 0.98 to 0.99. Cygnus X1, one of the first confirmed black holes, has a spin parameter of about 0.99. These black holes are spinning at more than 99% of the theoretical maximum. They are rotating so fast that the very fabric of spacetime around them is being dragged along for the ride. This brings us to one of the most mind-bending consequences of rotation in general relativity, the phenomenon known as frame dragging, also called the Lenz-Thirring effect. When a massive object rotates, it does not just sit in spacetime and spin. It actually drags spacetime itself along with it, like a spinning ball embedded in honey dragging the honey around as it turns. For ordinary objects like Earth, this effect is incredibly small, almost imperceptible. But it is real, and it has been measured. NASA's Gravity Probe B mission, launched in 2004, used 4 ultra-precise gyroscopes orbiting Earth to detect frame dragging. The effect was tiny, just 37 milliards per year, less than a degree over 1 million years. But it was there, exactly as Einstein's theory predicted. The Earth, simply by rotating, is dragging the fabric of spacetime around with it. But near a rapidly spinning black hole, frame dragging becomes extreme and dramatic. A rotating black hole is surrounded by a region called the ergosphere, from the Greek word ergon meaning work or energy. The ergosphere lies outside the event horizon, so you can enter it and still escape. But inside the ergosphere, frame dragging is so intense that spacetime itself is being dragged around the black hole faster than light would need to travel to stand still. In other words, inside the ergosphere, it is impossible to remain stationary. You are dragged along with the rotation of spacetime regardless of how much energy you expend trying to resist. Even light inside the ergosphere must rotate with the black hole. You cannot stand still inside the ergosphere. Spacetime itself is flowing past you, carrying you along with the black hole's rotation. This leads to one of the most brilliant theoretical ideas in the history of physics, proposed by Roger Penrose in 1969, which has come to be known as the Penrose process. Penrose realized that the ergosphere of a rotating black hole represents an incredible source of energy. Here is how it works. Imagine you send an object into the ergosphere. While inside the ergosphere, you split the object into two pieces. You arrange things so that one piece falls into the black hole on a retrograde orbit, that is, against the direction of the black hole's rotation. The other piece escapes back out of the ergosphere. The piece that falls in reduces the black hole's angular momentum, slowing its rotation slightly, but the piece that escapes comes out with more energy than the original object went in with. You have extracted energy from the black hole's rotation. The black hole spins a little slower, and you have gained energy. Penrose calculated that up to 29% of a black hole's total mass energy could be extracted this way. For a supermassive black hole, that represents more energy than entire galaxies produce in their lifetimes. The Penrose process is not just a theoretical curiosity. A related mechanism, the Blandford-Snarek process, proposed by Roger Blandford and Roman Snarek in 1977, is believed to be responsible for powering the most energetic sustained phenomena in the universe, the relativistic jets of active galactic nuclei and quasars. When a supermassive black hole at the center of a galaxy is surrounded by a hot, magnetized accretion disk, the combination of the black hole's rotation and the threading magnetic field extracts rotational energy from the black hole and channels it into two narrow, highly focused jets of plasma that shoot out from the poles at nearly the speed of light. These jets can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of the galaxy itself. They carry enormous amounts of energy, and they have a profound impact on the evolution of the galaxy and its surroundings, heating the intergalactic medium, suppressing or triggering star formation, and shaping the large-scale structure of the cosmic web. Let that sink in. The spinning of a single black hole, an object a few tens of kilometers across, can affect the evolution of structures millions of light years in extent. A black hole's rotation can reshape an entire galaxy. This is the power of angular momentum, the power of rotation, operating at its most extreme. When two black holes orbit each other and eventually merge, as has now been detected multiple times by the LIGO and Virgo gravitational wave observatories, the spins of the individual black holes play a crucial role in the dynamics of the merger and in the gravitational wave signal we detect. The way the spins are aligned relative to each other and relative to the orbital plane affects how the orbit evolves. How much energy is radiated as gravitational waves, and what the final merged black hole looks like. After the merger, the final black hole settles down into a stable rotating state through a process called ringdown, emitting gravitational waves at specific frequencies determined by its mass and spin, much like a bell emitting sound at specific frequencies determined by its shape and size. By analyzing the ringdown signal, scientists can measure the mass and spin of the final black hole with remarkable precision. This is yet another way that rotation reveals itself, encoded in the very ripples of spacetime itself. The spin of supermassive black holes at the centers of galaxies is now recognized as a key factor in galaxy evolution. The spin determines how efficiently the black hole can power jets, which in turn determines how much feedback energy is injected into the galaxy. High-spin black holes produce powerful jets that can shut down star formation in massive galaxies, explaining why the most massive galaxies in the universe are red and dead, full of old stars with very little new star formation. Low-spin black holes produce weaker jets and less feedback, allowing star formation to continue. The co-evolution of supermassive black holes and their host galaxies is one of the hottest topics in modern astrophysics, and spin is at the center of the story. Now let us zoom out to the grandest scale of rotation we can observe, the rotation of entire galaxies. Galaxies are enormous collections of stars, gas, dust, and dark matter, bound together by gravity. Our Milky Way contains roughly 200 to 400 billion stars spread across a disk about 100,000 light-years in diameter, and the whole thing is rotating. The Sun, located about 26,000 light-years from the galactic center, takes approximately 225 to 250 million years to complete one orbit around the galaxy. This period is sometimes called a galactic year or a cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 18 to 20 orbits around the galaxy. The dinosaurs roamed the Earth less than one galactic year ago. The rotation of the Milky Way, and of spiral galaxies in general, reveals one of the most startling and important discoveries in the history of astronomy: the discovery of dark matter. In the 1970s, astronomer Vera Rubin and her collaborator Kent Ford conducted a groundbreaking study of the rotation of spiral galaxies. They measured how fast stars at different distances from the galactic center were orbiting. According to Newtonian gravity, and also according to general relativity for systems of this type, stars farther from the center should orbit more slowly, just as planets farther from the Sun orbit more slowly. The Sun takes a year to orbit, while Neptune takes 165 years. You would expect the same pattern in galaxies: stars near the center orbit fast, stars at the edge orbit slow. This is what is called a Keplerian rotation curve, and it falls off with distance. But that is not what Rubin and Ford found. Instead, they discovered that the rotation curves of spiral galaxies are flat. Stars at the outer edge of a galaxy orbit at roughly the same speed as stars much closer to the center. This is deeply anomalous. It means there is much more mass in the outer regions of galaxies than we can see. The visible stars and gas are not nearly massive enough to produce the observed rotation speeds. Something invisible is providing the additional gravitational pull. That something is dark matter. Today we know that every galaxy is surrounded by an enormous halo of dark matter, a substance that does not emit, absorb, or reflect light, and whose nature remains one of the greatest mysteries in physics. The dark matter halo extends far beyond the visible galaxy, and it contains about 5 to 10 times more mass than all the visible matter combined. Roughly 85% of all matter in the universe is dark matter. And we discovered this through rotation, through the spinning of galaxies. Rotation revealed the invisible. The rotation of the Milky Way also explains the beautiful spiral arms that characterize spiral galaxies like our own. If you think about it, the existence of spiral arms is actually a puzzle. If the spiral arms were material structures, made of the same stars rotating at different speeds at different distances from the center, they would wind up over time due to differential rotation. After a few galactic rotations, the arms would be wound so tightly that they would be indistinguishable from the rest of the disk. This is called the winding problem. The solution, proposed independently by C.C. Lin and Frank Hsu in the 1960s, is that spiral arms are not material structures at all. They are density waves, like traffic jams on a highway. Cars slow down as they approach the jam and speed up as they leave it, so the jam persists even though the individual cars move through it. Similarly, stars and gas slow down as they enter a spiral arm region and speed up as they leave it. The spiral pattern persists even though the individual stars pass through it. The density wave compresses gas as it passes through, triggering star formation, which is why spiral arms are often outlined by bright, young blue stars and glowing nebulae. These young stars are born in the arms, shine brightly for a relatively short time, and die before they can move far from where they were born. The spiral arms are cosmic factories, using the density wave generated by the galaxy's rotation to compress gas and create new generations of stars. What happens when galaxies collide? This is not a hypothetical question, because the Milky Way and the Andromeda Galaxy are on a collision course, approaching each other at about 110 kilometers per second. In about 4 to 5 billion years, the two galaxies will begin to merge in a cosmic dance that will unfold over hundreds of millions of years. When galaxies merge, their rotations interact in complex ways. The angular momenta of the two galaxies can add together, partially cancel, or produce entirely new rotational patterns depending on the geometry of the collision. If two galaxies collide head-on with opposite spins, much of the angular momentum can cancel out, producing a slowly rotating or even non-rotating merger remnant. This is thought to be one of the main ways elliptical galaxies form. Elliptical galaxies, which are roughly football-shaped and lack the defined disk and spiral structure of spiral galaxies, have much less net rotation than spiral galaxies. Many of them are thought to be the products of major mergers that scrambled and partially cancelled the angular momenta of the original galaxies. There is a fascinating and still poorly understood observation about galaxy spins at the largest scales. Several studies have found hints that galaxy rotation axes are not randomly oriented, but instead tend to align with the large-scale structure of the cosmic web, the vast network of filaments and voids that forms the skeleton of the universe. Galaxies embedded in cosmic filaments tend to have their spin axes aligned either parallel or perpendicular to the filament, depending on their mass. If confirmed, this would mean that the rotational properties of individual galaxies are connected to the structure of the universe on scales of hundreds of millions of light years. The tidal torque theory predicts some degree of alignment because the same tidal forces that gave galaxies their spin are related to the large-scale structure. But the observed degree of alignment has sometimes been larger than expected, hinting at physics beyond our current models. This is an active area of research, with new surveys and simulations continually refining our understanding. Now we are going to take a sharp turn in scale. We have gone from the Big Bang to galaxies, from galaxies to stars, from stars to planets. We have explored the grandest scales of rotation in the cosmos. But now, we are going to plunge all the way down to the smallest scale imaginable. Smaller than atoms, smaller than protons, smaller than anything you can visualize. We are going to enter the quantum realm, and here we will discover that rotation, or something astonishingly like it, exists at the very foundation of reality in a way that is stranger and more profound than anything we have encountered so far. Every fundamental particle in the universe, every electron, every quark, every photon, every neutrino, possesses a property called spin. The name suggests rotation, and in many ways, spin behaves exactly like angular momentum. A particle with spin responds to magnetic fields just as a rotating charged object would. Spin can be transferred between particles in collisions, just as angular momentum is transferred between colliding objects. Spin obeys conservation laws identical to those of angular momentum, and yet quantum spin is not actual physical rotation. An electron is, as far as we can determine, a point particle. It has no spatial extent, it has no surface, it has no internal structure that could possibly be rotating. If you try to model the electron as a tiny spinning ball, you quickly run into contradictions. The surface of the ball would need to be moving faster than the speed of light to generate the observed angular momentum, which is physically impossible. Quantum spin is not the spinning of anything. It is an intrinsic, fundamental property of the particle, as basic and irreducible as its mass or its electric charge. It simply is. The discovery of spin is one of the great stories of 20th century physics. In 1922, Otto Stern and Wolfgang Gerlach performed an experiment that would reveal the existence of quantum spin, though they did not fully understand what they had found at the time. They sent a beam of silver atoms through a non-uniform magnetic field. According to classical physics, if the atoms had randomly oriented magnetic moments from some form of angular momentum, they should spread out into a continuous band on the detector. But instead, the beam split into two distinct spots. 2. Not a continuous spread, but two sharp, well-defined spots. This meant that the angular momentum of the silver atoms was not random and continuous, but was quantized, meaning it could only take on specific, discrete values. For the outer electron of the silver atom, there are only two possible orientations: spin up and spin down. Nothing in between. This quantization of angular momentum was a stunning confirmation that the quantum world operates by rules fundamentally different from the classical world. The mathematical description of spin was provided by Paul Dirac in 1928 when he formulated his famous Dirac equation, which combined quantum mechanics with special relativity. The Dirac equation naturally and automatically predicted the existence of spin as a consequence of requiring quantum mechanics to be consistent with Einstein's theory of special relativity. Spin was not put into the equation by hand. It emerged naturally from the mathematics. This was one of the most beautiful and profound moments in the history of physics. When you demand that quantum mechanics respect the symmetries of special relativity, spin appears automatically. It is not an add-on or an afterthought. It is a fundamental consequence of the structure of spacetime itself. Particles come in two broad categories based on their spin. Fermions are particles with half-integer spin, 1/2, 3/2, 5/2, and so on. Electrons, quarks, protons, and neutrons are all fermions with spin 1/2. Bosons are particles with integer spin, 0, 1, 2, and so on. Photons have spin 1. Gluons have spin 1. The Higgs boson has spin 0. The hypothetical graviton would have spin 2. This distinction between fermions and bosons is not just a classification scheme. It is the deepest division in the particle world, and it has consequences that are nothing short of cosmic. Fermions obey the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle states that no two identical fermions can occupy the same quantum state at the same time. Two electrons in an atom cannot have the same set of quantum numbers. This single rule, which is a direct consequence of their half-integer spin, is responsible for essentially all of the structure and complexity in the universe. It is why the periodic table of elements exists. It is why atoms have electron shells that fill up in specific patterns. It is why different elements have different chemical properties. It is why chemistry works the way it does. It is why solid objects are solid and cannot pass through each other. It is why matter has structure at all. Without the Pauli exclusion principle, all electrons in an atom would collapse into the lowest energy state, and all atoms would be identical, inert, and unable to form molecules, minerals, or living organisms. Without spin, there would be no chemistry, no biology, no stars as we know them. The structure of the entire physical world, from the atoms in your body to the stars in the sky, rests on the foundation of quantum spin. Bosons, on the other hand, are social. They do not obey the Pauli exclusion principle and can pile up in the same quantum state in unlimited numbers. This is what allows lasers to work, because photons are bosons and millions of them can occupy the same quantum state, producing coherent light. It is also what allows phenomena like Bose-Einstein condensation, where a collection of bosonic atoms cooled to near absolute zero all fall into the same quantum state, behaving as a single quantum entity that can be large enough to see with the naked eye. The difference between fermions and bosons, between the particles that make up matter and the particles that carry forces, comes down entirely to spin. Half-integer versus integer. This is the spin statistics theorem, proven by Wolfgang Pauli in 1940, and it is one of the deepest and most consequential results in all of theoretical physics. Now here is something about quantum spin that is genuinely mind-bending, something that has no analogy in everyday experience. A particle with spin 1/2, like an electron, has a bizarre geometric property. If you rotate it by 360 degrees, it does not come back to its original state. Instead, its quantum state picks up a negative sign. It is multiplied by -1. To return it to its original state, you need to rotate it by 720 degrees, 2 full turns. This is profoundly strange. Every object in our everyday experience returns to its original configuration after a single 360-degree rotation. Spin it once, and it is back where it started. But an electron needs to be spun twice to get back to where it started. After one full rotation, it is in a state that is, in a precise mathematical sense, the negative of its original state. It takes 2 full rotations for the state to return to the original. There is a physical demonstration of this called the Dirac belt trick, or the plate trick. Hold a plate flat on your palm, rotate it 360 degrees, keeping it flat. Your arm is now twisted. Now continue rotating the plate another 360 degrees in the same direction. Your arm untwists. After 720 degrees, everything is back to normal. After 360 degrees, things were twisted. This is an analogy, not a perfect explanation, but it captures something of the mathematical structure. Objects with this property are described by what mathematicians call spinors, and they are fundamentally different from ordinary vectors and tensors. Spinors are the natural mathematical language for describing fermions, and their double rotation property is deeply connected to the topology of rotation in 3-dimensional space. Quantum spin also gives rise to magnetism. A spinning charged particle is essentially a tiny current loop, and current loops produce magnetic fields. The electron's spin gives it a magnetic moment, making each electron a tiny magnet. In most materials, these tiny magnets point in random directions and cancel out. But in ferromagnetic materials like iron, the electron spins can align, producing a macroscopic magnetic field. Every magnet you have ever picked up, every compass needle that has ever pointed north, owes its magnetism to the quantum spin of electrons. And spin is the basis of one of the most transformative technologies in medicine, magnetic resonance imaging, or MRI. The protons in the nuclei of hydrogen atoms have spin 1/2, and therefore have a magnetic moment. When placed in a strong external magnetic field, these proton spins align either with or against the field. A radio frequency pulse can flip the spins, and when they relax back, they emit signals that depend on the chemical environment of the hydrogen atoms. By analyzing these signals, MRI machines construct detailed images of the inside of the human body without any harmful radiation. Every time a patient gets an MRI scan, they are benefiting directly from quantum spin, the bizarre, counterintuitive, mathematically abstract property of subatomic particles is saving lives every day. Spin is also the basis of one of the most famous and philosophically provocative phenomena in quantum mechanics, quantum entanglement. When 2 particles interact and then separate, their quantum states can become correlated in ways that have no classical explanation. If you measure the spin of one particle and find it is spin up, you instantly know the other particle's spin is spin down, regardless of how far apart they are. This correlation is instantaneous, appearing to act faster than light, which deeply troubled Einstein. He called it spooky action at a distance, and argued, along with Boris Podolsky and Nathan Rosen, in their famous 1935 paper, that quantum mechanics must be incomplete. Surely, he argued, the particles must have had definite spins all along, and measuring one simply reveals what was already true. This would mean quantum mechanics is just a statistical description of some deeper hidden reality. But in 1964, physicist John Bell proved a remarkable theorem showing that if Einstein was right and hidden variables existed, then certain experimental measurements would have to obey specific mathematical inequalities. If quantum mechanics was correct and no hidden variables existed, these inequalities would be violated. Experiments, first by John Clauser and Alain Aspect and many others since, have decisively shown that Bell's inequalities are violated. Nature does not have hidden variables in the way Einstein imagined. The correlations between entangled particle spins are genuinely non-local. The measurement of one particle truly does affect the state of the other, instantly regardless of distance. This is not science fiction. This is experimentally verified fact. And it all revolves around spin. Spin is the property most commonly used in entanglement experiments, and spin correlations are the most direct test of quantum non-locality. Entangled spins are now being harnessed for quantum computing, quantum cryptography, and quantum teleportation, technologies that may revolutionize the 21st century. Is there a connection between quantum spin at the subatomic level and the macroscopic rotation of planets, stars, and galaxies? This is a deep and subtle question. In one sense, no. Quantum spin is an intrinsic property of point particles that does not correspond to physical rotation. The spin of an electron is fundamentally different from the spin of the Earth. They are governed by different physical laws and operate at vastly different scales. But in another sense, yes, there are profound connections. Both quantum spin and macroscopic angular momentum are manifestations of the same fundamental symmetry of nature, rotational symmetry, and both are conserved for the same reason, Noether's theorem, which we will come to shortly. Furthermore, some theoretical frameworks, notably Roger Penrose's twistor theory, suggest that spacetime itself may be fundamentally constructed from spinorial objects whose basic mathematical description involves spin. In this view, spin is not just a property of particles embedded in spacetime. Spin is spacetime at the deepest level. This remains a speculative and incomplete idea, but it hints at a unity between quantum spin and cosmic rotation that we are only beginning to glimpse. Now let us go even deeper into the relationship between rotation and the fabric of spacetime itself. We have already mentioned frame dragging, the phenomenon by which rotating objects drag spacetime around with them. But the full story is richer and more profound than what we have covered so far. Einstein's general theory of relativity, published in 1915, describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive objects bend the geometry of spacetime around them, and other objects follow the straightest possible paths through this curved geometry. These paths are called geodesics, and what we perceive as the force of gravity is actually objects following geodesics through curved spacetime. But when a massive object rotates, it does something extra. It does not just curve spacetime, it twists it. It drags spacetime along in the direction of its rotation. This was first predicted by Joseph Lense and Hans Thirring in 1918, just 3 years after Einstein published general relativity, and it is known as the Lense-Thirring effect or frame dragging. The idea is that a rotating mass creates a swirl in spacetime, much like a spinning ball creates a swirl in a viscous fluid surrounding it. Objects near a rotating mass will be influenced by this swirl. Their orbits will precess, their orientation will shift, and if they are close enough, they will be dragged along irresistibly. For slowly rotating, weakly gravitating objects like Earth, frame dragging is tiny. As mentioned, gravity probe B measured it to be about 37 milliseconds per year. This is an incredibly subtle effect, and measuring it required some of the most precise instruments ever built. The gyroscopes on gravity probe B were the most perfect spheres ever manufactured by humanity, polished to within 40 atomic layers. They were made of fused quartz and coated with a thin layer of niobium so they could be monitored using superconducting quantum interference devices. The entire satellite had to be maintained at cryogenic temperatures and shielded from every possible disturbance. The fact that frame dragging was successfully measured under these challenging conditions is a triumph of experimental physics and a stunning confirmation of general relativity. But near a rapidly spinning black hole, frame dragging is not subtle at all. It is dramatic, extreme, and dominant. We have already discussed the ergosphere, the region where spacetime is dragged so violently that nothing can remain stationary. But the effects go further. Frame dragging near a spinning black hole causes the orbits of particles and light to precess, causes accretion disks to warp and twist, and creates phenomena that simply do not exist around non-rotating black holes. The shadow of a spinning black hole the dark silhouette that the Event Horizon Telescope famously imaged for the M87 black hole in 2019, is asymmetric because of frame dragging. One side of the accretion disk appears brighter than the other because the rotation of spacetime affects how light reaches us. The very image of a black hole encodes information about its spin. There is a deep philosophical question associated with rotation and spacetime that has been debated for centuries. Is rotation absolute or relative? Newton argued that rotation is absolute, meaning you can tell whether something is rotating without reference to anything else. His famous bucket experiment illustrated this. If you spin a bucket of water, the water climbs up the sides, forming a concave surface. This happens regardless of what else is happening in the universe. You can tell the water is rotating because it is pushed outward. Newton argued that this proves the existence of absolute rotation relative to absolute space itself. But the Austrian physicist and philosopher Ernst Mach challenged this view in the late 19th century. Mach argued that what we call inertia, the tendency of objects to resist changes in their motion, is not determined by absolute space, but by the distribution of all the matter in the universe. According to Mach's principle, as it came to be called, the reason the water in Newton's bucket knows it is rotating is that it is rotating relative to the distant stars and galaxies. If all the matter in the universe were somehow removed, rotation would lose its meaning. There would be no way to tell if the water was spinning or the universe was spinning around the water. The two situations would be physically identical. Einstein was deeply inspired by Mach's principle when developing general relativity. He hoped that his theory would fully incorporate Mach's ideas, making inertia entirely determined by the matter content of the universe. In the end, general relativity partially incorporates Mach's principle, but not entirely. Frame dragging is a Machian effect, because the rotation of nearby matter does influence local inertial frames. But general relativity also allows solutions with rotation in otherwise empty spacetime, which is decidedly non-Machian. The debate about whether rotation is truly relative or has some absolute character continues to this day, and it touches on some of the deepest questions about the nature of space, time, and existence. Let us now explore some of the more unusual and surprising manifestations of rotation in the universe, because rotation is not always orderly and predictable. Sometimes it is chaotic, counterintuitive, and downright bizarre. Consider Hyperion, a moon of Saturn. Most moons in the solar system rotate in a regular, predictable way. They spin steadily around an axis that remains more or less fixed in space. But Hyperion does not. Hyperion tumbles chaotically. Its rotation axis wanders randomly, and its rotation rate varies unpredictably from one orbit to the next. If you were standing on Hyperion and looked up at Saturn, you would see it in a different part of the sky every day, at a different angle, sometimes rising in the east and sometimes in the west. This is genuine mathematical chaos, the first ever confirmed case of chaotic rotation in the solar system. The reason for this chaos is Hyperion's irregular, potato-like shape combined with its eccentric orbit and the gravitational influence of nearby Titan, Saturn's largest moon. These factors create a situation where tiny differences in Hyperion's initial conditions lead to wildly different rotational outcomes, the hallmark of chaotic dynamics. Then there is the YOUR effect, which stands for Yarkovsky-O'Keefe-Radzievskii-Paddock effect, and yes, that is a mouthful. This is a phenomenon in which sunlight can change the rotation of a small asteroid over time. Here is how it works. An irregularly shaped asteroid absorbs sunlight on its surface and re-emits the energy as thermal radiation, as heat. Because the asteroid is irregularly shaped, this thermal radiation is not emitted uniformly in all directions. The slight asymmetry in the thermal emission creates a tiny torque on the asteroid, gradually spinning it up or down over millions of years. This effect is minuscule, but over long timescales, it can significantly alter an asteroid's rotation rate. Some asteroids have been spun up to rotation periods of just a few minutes, so fast that they are on the verge of disintegrating. The only thing holding them together is the cohesive strength of their material, which tells us something about their internal structure. Asteroids that are loose piles of rubble, so-called rubble pile asteroids, cannot spin very fast because they would fly apart. The observed distribution of asteroid rotation rates reveals a clear spin barrier at about 1 rotation per 2.2 hours for asteroids larger than about 150 meters. Faster than this, and a rubble pile cannot hold together. Asteroids smaller than this limit can spin much faster, suggesting they are monolithic, solid rocks rather than rubble piles. Earth's own rotation is not as smooth and steady as you might think. Our planet wobbles as it spins, in a phenomenon called the Chandler wobble, discovered by Seth Carlo Chandler in 1891. The Earth's rotation axis traces out a small circle relative to the body of the Earth, with a period of about 433 days and an amplitude of about 9 meters at the poles. This wobble exists because the Earth is not a perfectly rigid body. It deforms slightly, and its mass distribution changes due to earthquakes, post-glacial rebound, ocean circulation, and atmospheric pressure changes. The Chandler wobble has been observed for over a century, and yet the mechanism that sustains it against dissipation is still debated. Something must be continually exciting the wobble, feeding it energy, because internal friction should damp it out in a few decades. The leading candidates for the excitation mechanism are fluctuations in ocean bottom pressure and atmospheric pressure changes, but the question is not fully settled. Earth's rotation is also irregular on shorter timescales. Earthquakes can slightly alter the planet's rotation by redistributing mass. The 2011 magnitude 9.0 earthquake in Japan shortened the day by about 1.8 microseconds by shifting mass closer to Earth's axis. The 2004 Indian Ocean earthquake shortened the day by a similar amount. Seasonal variations in atmospheric and oceanic circulation cause the length of day to vary by about a millisecond over the course of a year. And on longer timescales, the exchange of angular momentum between Earth's core and mantle causes decade-scale fluctuations in Earth's rotation rate. These variations are small but measurable, and they create practical challenges for timekeeping. Our civil time system is based on atomic clocks, which tick at a perfectly steady rate, but the Earth's rotation, which defines the astronomical day, is variable. To keep these two time systems in agreement, leap seconds have been periodically added to our clocks since 1972. As of 2024, 27 leap seconds had been added. The decision about when to add a leap second is made by the International Earth Rotation and Reference System Service, based on precise measurements of Earth's rotation. However, in a landmark decision, the General Conference on Weights and Measures voted in 2022 to abolish leap seconds by 2035, because they cause complications for precision technology systems like GPS, telecommunications, and financial trading. Instead, a larger correction will be allowed to accumulate and be applied less frequently. Perhaps the most visually stunning and conceptually mind-bending rotational phenomenon in classical mechanics is the Dzhanibekov Effect, also known as the tennis racket theorem or the intermediate axis theorem. In 1985, Soviet cosmonaut Vladimir Dzhanibekov observed something extraordinary aboard the Salyut 7 space station. He was unpacking supplies and removed a wing nut by spinning it off a bolt. In the microgravity environment of the space station, the wing nut continued to spin freely in the air. But as Dzhanibekov watched, the wing nut did something completely unexpected. Every few rotations, it spontaneously flipped. It would spin steadily for a while, then suddenly flip 180 degrees, then spin steadily again, then flip again, in a regular, periodic, and deeply strange pattern. This phenomenon can be understood through the mathematics of rigid body rotation, specifically Euler's equations. Any rigid body has three principal axes of rotation, corresponding to the maximum, minimum, and intermediate moments of inertia. Rotation around the axis of maximum moment of inertia is stable. Rotation around the axis of minimum moment of inertia is also stable. but rotation around the axis of intermediate moment of inertia is unstable. Any tiny perturbation will grow, causing the object to flip. This is the intermediate axis theorem, and it is why a tennis racket, when tossed in the air with a spin around its intermediate axis, will flip. It is why a book, when spun around its intermediate axis, tumbles unpredictably. And it is why Dzhanibekov's wing nut flipped periodically in space. The Dzhanibekov effect gained widespread public attention when it was explained in a popular science video, and it sparked a common question. Could the same thing happen to Earth? Could our planet suddenly flip its rotation axis? The short answer is no. Earth is spinning around its axis of maximum moment of inertia, which is the stable axis. The equatorial bulge ensures that Earth's moment of inertia is greatest around its current rotation axis. Perturbations will cause small wobbles like the Chandler wobble, but not a catastrophic flip. The Dzhanibekov effect only applies to objects spinning around their intermediate axis, which Earth is not. So while the physics is real and dramatic, it poses no threat to our planet. Let us now discuss one of the most important and pervasive consequences of rotation that affects our daily lives: the Coriolis effect. The Coriolis effect is a so-called fictitious force that appears in rotating reference frames. Because Earth is rotating, objects moving across its surface experience a deflection. In the northern hemisphere, moving objects are deflected to the right. In the southern hemisphere, they are deflected to the left. This is not a real force in the sense that no physical object is pushing on the moving thing. It is an apparent force that arises because we are observing the motion from a rotating frame of reference. But its effects are very real and very important. The Coriolis effect is the primary reason large-scale weather systems rotate. Low-pressure systems in the northern hemisphere rotate counterclockwise, while those in the southern hemisphere rotate clockwise. This is why hurricanes, typhoons, and cyclones rotate the way they do. Without Earth's rotation, these organized rotating weather systems simply could not exist. The Coriolis effect also drives the global ocean circulation patterns, the jet stream, and the trade winds. It is one of the most important factors in determining weather and climate on Earth, and it exists solely because our planet rotates. There is a common myth that the Coriolis effect determines the direction water drains in sinks and toilets, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This is false, or at least vastly overstated. The Coriolis effect is proportional to the velocity of the moving object, the rotation rate of the Earth, and the sign of the latitude. For a small body of water draining from a sink, the Coriolis force is incredibly tiny, many orders of magnitude smaller than other forces acting on the water, such as the shape of the basin, residual currents from filling, and asymmetries in the drain. In carefully controlled experiments where all other influences are eliminated, the Coriolis effect can determine the direction of drainage. But in an ordinary sink or toilet, it is completely overwhelmed by other factors. The direction your toilet water swirls is determined by the design of the toilet, not by which hemisphere you are in. The Coriolis effect does, however, have important practical implications beyond weather. Long-range artillery and sniper shots must account for the Coriolis deflection, which can amount to several meters over the distance of a few kilometers. The military takes this very seriously. During World War I, the British reportedly failed to account for the Coriolis effect in a naval engagement in the South Atlantic, causing their shells to miss to the left. The Coriolis effect also affects aircraft navigation, rocket launches, and the trajectories of ballistic missiles. One of the most elegant demonstrations of Earth's rotation is Foucault's pendulum, first demonstrated by French physicist Lon Foucault in 1851 in the Pantheon in Paris. Foucault suspended a heavy bob from a long wire and set it swinging. Over the course of hours, the plane of the pendulum's swing appeared to rotate, slowly tracing out a circular pattern on the floor. Of course, the pendulum's plane of swing was not actually rotating. A pendulum once set in motion swings in a fixed plane in inertial space. It was the Earth that was rotating beneath the pendulum, gradually changing the orientation of the building relative to the pendulum's fixed swing plane. At the north or south pole, the pendulum's plane would complete a full rotation in exactly 24 hours. At the equator, it would not rotate at all. At intermediate latitudes, it rotates at a rate that depends on the latitude. Foucault's pendulum was the first direct visual proof that the Earth rotates, and large Foucault pendulums can still be seen in science museums around the world. Now let us discuss the mathematical foundation that underlies all of rotational physics, the reason angular momentum is conserved, and arguably the deepest and most beautiful insight in all of physics. I am talking about Noether's theorem, proved by the brilliant mathematician Emmy Noether in 1915 and published in 1918. Noether's theorem states that every continuous symmetry of the laws of physics corresponds to a conserved quantity. This is one of those statements that sounds simple, but contains an almost unfathomable depth of meaning. What is a symmetry of the laws of physics? It means that the laws of physics do not change when you perform a certain transformation. For example, the laws of physics are the same today as they were yesterday and as they will be tomorrow. This is time translation symmetry. According to Noether's theorem, this symmetry corresponds to the conservation of energy. Energy is conserved because the laws of physics do not change with time. Similarly, the laws of physics are the same here as they are a meter to the left or a mile to the north. This is spatial translation symmetry, and it corresponds to the conservation of linear momentum. Momentum is conserved because the laws of physics do not change from place to place. And now, the one most relevant to our story. The laws of physics are the same regardless of which direction you face. If you perform an experiment facing north, and then perform the same experiment facing east, you get the same results. This is rotational symmetry, and according to Noether's theorem, it corresponds to the conservation of angular momentum. Angular momentum is conserved because the laws of physics are rotationally symmetric. That is it. That is the deepest reason why everything in the universe rotates, and why that rotation persists. The universe does not care which direction you face. The laws of physics are the same in every direction. And this simple, beautiful symmetry, this rotational invariance of the laws of nature, mathematically guarantees the conservation of angular momentum. And the conservation of angular momentum, combined with the fact that gravitational collapse of non-uniform matter inevitably produces some angular momentum, guarantees that everything in the universe rotates. Noether's theorem is often called the most important theorem in physics. It connects symmetry to conservation laws with absolute mathematical rigor. It is the reason we believe angular momentum conservation is exact and inviolable, not just an approximation. As long as the laws of physics have rotational symmetry, angular momentum will be conserved. And we have no reason to believe the laws of physics ever violate rotational symmetry. It is built into the very structure of spacetime. Emmy Noether herself deserves recognition in this narrative. She was one of the greatest mathematicians of the 20th century, yet she faced tremendous obstacles because of her gender. For years, she was not allowed to hold an official academic position in Germany, despite the support of mathematical luminaries like David Hilbert and Felix Klein. She taught unpaid and had her lectures listed under Hilbert's name. When she was finally granted a position, she was paid a pittance. She fled Nazi Germany in 1933 because of her Jewish heritage, and died just 2 years later in the United States at the age of 53. Einstein himself wrote in her obituary that she was the most significant creative mathematical genius thus far produced since the higher education of women began. The theorem that bears her name is the foundation on which all conservation laws in physics rest, and it is one of the most profound insights any human has ever had about the nature of reality. Now I want to take a step back from the physics and mathematics and consider something that might seem surprising, the role of rotation in making life possible. We have already touched on some of these connections, but the full picture is even more remarkable than what we have covered so far. Earth's rotation is essential for life in ways that go far beyond the day-night cycle. Yes, the alternation of day and night prevents one hemisphere from overheating while the other freezes, creating a more habitable overall temperature distribution. But the effects run much deeper. Earth's rotation drives the Coriolis effect, which, as we discussed, is responsible for large-scale weather patterns, ocean currents, and the redistribution of heat from the equator to the poles. Without this redistribution, the equator would be much hotter and the poles much colder, making a much smaller fraction of the planet habitable. The Coriolis-driven ocean currents, such as the Gulf Stream, transport vast amounts of heat and moderate the climates of entire continents. Europe, for instance, is much warmer than it would otherwise be at its latitude, thanks to the Gulf Stream, and the Gulf Stream exists because of Earth's rotation. Perhaps most critically, Earth's rotation is responsible for our planet's magnetic field. The Earth has a liquid iron outer core that is electrically conducting. The rotation of the Earth, combined with convection currents in the outer core, driven by heat from the solid inner core, creates a self-sustaining dynamo that generates Earth's magnetic field. This is the geodynamo, and it is one of the most important processes in planetary science. Without the geodynamo, Earth would have no global magnetic field. And without a magnetic field, we would be defenseless against the solar wind, a stream of charged particles flowing from the sun at hundreds of kilometers per second. The solar wind, unchecked by a magnetic field, would gradually strip away a planet's atmosphere through a process called sputtering. This is exactly what happened to Mars. Mars once had a thick atmosphere and liquid water on its surface, but its core cooled and solidified, its dynamo shut down, its magnetic field disappeared, and the solar wind slowly eroded its atmosphere over hundreds of millions of years, leaving it the thin-atmosphered, cold, barren world we see today. Earth's magnetic field, generated by its rotation, shields us from this fate. It deflects the solar wind, channels it toward the poles where it creates the beautiful auroras, and preserves our atmosphere and oceans. Without rotation, no dynamo. Without the dynamo, no magnetic field. Without the magnetic field, no atmosphere. Without an atmosphere, no life. Rotation is not just a curiosity. It is a prerequisite for our existence. The Moon plays a crucial role in this story as well. As we discussed, the Moon was formed from a giant impact that also affected Earth's rotation. But the Moon's most important contribution to habitability may be its stabilizing effect on Earth's axial tilt. Earth's axis is currently tilted at about 23.4 degrees relative to its orbital plane, and this tilt is responsible for the seasons. Without the Moon's gravitational influence, Earth's axial tilt would be unstable, varying chaotically between 0 and about 85 degrees over millions of years. At zero tilt, there would be no seasons, and the equator would be perpetually hotter than the poles. At 85 degrees, the seasons would be extreme, with each hemisphere alternating between pointing almost directly at the sun for half the year and pointing almost directly away for the other half. These wild variations in axial tilt would cause correspondingly wild variations in climate, making it much more difficult for complex life to evolve and persist. Mars, which has no large moon, has experienced exactly this kind of chaotic axial tilt variation. Its tilt has swung from near zero to over 60 degrees and back again over its history. The Moon's gravitational influence keeps Earth's tilt stable within a narrow range, between about 22.1 and 24.5 degrees, with a period of about 41,000 years. This stability is essential for the relatively stable climate that has allowed complex life to flourish on Earth. Rotation appears in biology itself in profound and surprising ways. The molecules of life exhibit a property called chirality, or handedness. Many biological molecules come in two mirror image forms, like left and right hands. These are called enantiomers. Remarkably, life on Earth uses almost exclusively left-handed amino acids and right-handed sugars. This is one of the great unsolved mysteries of biology. Why did life choose one-handedness over the other? In a symmetric universe, you would expect equal amounts of both. Several hypotheses have been proposed. One of the most intriguing involves the weak nuclear force, one of the 4 fundamental forces of nature. The weak force is the only fundamental force that violates parity symmetry, meaning it distinguishes between left and right. Specifically, the weak force preferentially produces left-handed particles and right-handed antiparticles. This parity violation could, through a chain of subtle effects, have produced a slight excess of one-handedness of biological molecules in the pre-Bartic chemistry of the early Earth. And parity violation in the weak force is intimately connected to quantum spin, because parity is a symmetry under spatial inversion, and the weak force's violation of parity is directly related to how it interacts differently with left-spinning and right-spinning particles. So it is at least possible that the handedness of life on Earth, the fact that your proteins are built from left-handed amino acids rather than right-handed ones, traces back ultimately to quantum spin and the asymmetry of the weak nuclear force. DNAR itself is a beautiful example of rotation at the molecular level. The famous double helix discovered by James Watson, Francis Crick, Rosalind Franklin and Maurice Wilkins is a spiral, a rotating structure. The 2 strands of DNAR wind around each other in a right-handed helix, completing 1 full turn every 10 base pairs, a distance of about 3.4 nanometers. This helical structure is not arbitrary. It is determined by the angles and lengths of the chemical bonds between the nucleotide building blocks. When DNAR is replicated, the 2 strands must be unwound, separated, and copied by molecular machines called helicases and polymerases. These machines literally rotate the DNAR as they work, spinning it like a thread being unwound from a spool. Rotation at the molecular scale is essential for the continuation of life. Now let us consider the question of life on other worlds, where rotation is very different from what we experience on Earth. Tidally locked planets, those that always show the same face to their star, are expected to be extremely common, especially around red dwarf stars. Red dwarfs are the most abundant type of star in the galaxy, comprising about 70% of all stars. And their habitable zones, the regions where liquid water could exist on a planet's surface, are much closer to the star than Earth is to the Sun. At these close distances, tidal forces are strong, and planets are quickly driven into tidal locking, with one hemisphere in perpetual daylight and the other in perpetual darkness. For a long time, it was assumed that tidally locked planets would be inhospitable to life. The day side would be blisteringly hot, the night side would be frozen solid, and the atmosphere might even freeze out on the dark side. But more recent climate modelling has painted a more optimistic picture. If the planet has a sufficiently thick atmosphere, heat can be redistributed from the day side to the night side by powerful atmospheric circulation, creating a band of habitable conditions around the terminator, the boundary between day and night. Some models suggest that oceans on such worlds could remain liquid over a significant fraction of the surface. Whether life could arise and thrive under such conditions is an open question, but the answer is probably yes, at least for simple life. Complex life might be more challenging, but nature has repeatedly surprised us with its ability to adapt to extreme conditions. Let us now consider how humanity has harnessed rotation throughout our history, from the earliest days of civilization to the cutting edge of space technology. The story of human engagement with rotation is, in many ways, the story of technological civilization itself. The wheel, perhaps the most important mechanical invention in human history, is fundamentally a device that exploits rotation. Invented around 3500 BC in Mesopotamia, the wheel revolutionized transportation, agriculture, pottery, and manufacturing. Before the wheel, moving heavy objects required dragging them along the ground, fighting friction every inch of the way. The wheel converts this sliding friction into rolling friction, which is vastly lower, and channels it into rotational motion around an axle. This simple principle transformed human civilization, enabling carts, chariots, wagons, and eventually trains, cars, and aircraft, all of which rely on rotating wheels to move. The flywheel is another ancient application of rotation that remains important today. A flywheel is simply a heavy wheel that stores energy in its rotation. Because of conservation of angular momentum, a spinning flywheel resists changes in its rotation rate, smoothing out fluctuations in energy input and output. Ancient potters used flywheels to maintain the steady rotation of their pottery wheels. Industrial-era engineers used massive flywheels to smooth the power output of steam engines. And today, advanced flywheel energy storage systems using carbon fiber rotors spinning at tens of thousands of RPM in vacuum chambers are being developed as alternatives to battery storage for the electrical grid. The principle is the same as it was 5,000 years ago. Store energy in rotation and release it when needed. Gears, another ancient invention, are devices for transmitting and modifying rotational motion. A large gear driving a small gear produces a speed increase at the cost of reduced torque. A small gear driving a large gear produces a torque increase at the cost of reduced speed. Gear trains allow the precise control and conversion of rotational motion, and are the basis of clockwork, mechanical computers, vehicle transmissions, and countless other machines. The Antikythera mechanism, a remarkable ancient Greek device dating to about 100 BC and recovered from a shipwreck, is essentially a complex gear train that modelled the motions of the sun, moon, and planets. It is sometimes called the first analog computer, and it was powered entirely by hand-cranked rotation. Gyroscopes are perhaps the most elegant technological application of rotational physics. A gyroscope is a spinning wheel or disc whose axis of rotation resists being tilted. This resistance is a consequence of conservation of angular momentum. A spinning gyroscope, if tilted, will precess, slowly rotating its axis of spin around the direction of the applied torque, rather than simply falling over. This gyroscopic stability makes spinning objects excellent reference directions, and this property has been exploited extensively in navigation. Ship gyroscopes, aircraft gyroscopes, and spacecraft gyroscopes all use this principle to maintain orientation and sense rotation. Modern versions, such as ring laser gyroscopes and fiber optic gyroscopes, use the Dzhanibekov effect, in which two beams of light travel in opposite directions around a loop and interfere to reveal any rotation of the loop, to achieve extraordinary precision without any moving parts. In spacecraft, rotation is used for attitude control, the control of which direction the spacecraft is pointing. Because space is a vacuum with no friction, you cannot steer a spacecraft by pushing against the air. Instead, spacecraft use reaction wheels, spinning flywheels that can be sped up or slowed down to transfer angular momentum to or from the spacecraft. By speeding up a reaction wheel, the spacecraft itself slows down in the opposite direction, and vice versa. This allows extremely precise pointing without using fuel. The Hubble Space Telescope uses reaction wheels to point at specific targets with exquisite accuracy. The James Webb Space Telescope uses a similar system, and the Kepler Space Telescope, which discovered thousands of exoplanets, used reaction wheels to maintain the stable pointing required to detect the tiny dips in starlight caused by planets passing in front of their host stars. When 2 of Kepler's 4 reaction wheels failed, the mission was nearly lost. But ingenious engineers figured out how to use the remaining 2 wheels plus the pressure of sunlight to maintain enough stability for a modified mission. Even sunlight, through the tiny force of radiation pressure, can be used as a source of torque. Rotation in all its forms is the key to navigation and control in space. Some of the earliest spacecraft used spin stabilization, the simplest form of attitude control. By setting the entire spacecraft spinning around an axis, conservation of angular momentum keeps that axis stable in space, like a gyroscope. This was used by many early satellites and is still used by some spacecraft today, including certain interplanetary probes and some military satellites. The spin axis points in a fixed direction, and instruments mounted on the spacecraft sweep around as it spins, surveying the sky in a circular pattern. Looking to the future, rotation may be the key to enabling long-duration human space travel and permanent habitation in space. The problem of microgravity is one of the most serious challenges facing future space explorers. In the weightless environment of orbit, the human body deteriorates. Bones lose density. Muscles atrophy. The cardiovascular system weakens. Vision can be impaired. The immune system may be compromised. On a mission to Mars, lasting 6 to 9 months each way, astronauts would arrive in significantly degraded physical condition. And on a permanent space station or space colony, the health effects of long-term microgravity would be even more severe.